Today I'd like to introduce my project in this semester. My project is to reproduce and evaluate the result of the paper, online blind reverberation time estimation using CIN. Here's an overview of today's presentation. I'll begin with the abstract and the background, then explain the CIN model architecture. After that, I will introduce how the training data was generated and preprocessed. Then we'll look at the training process, result, and evaluation. And finally, wrap up with the conclusions and possible future directions. Reverberation time, or T60, is a key acoustic parameter used in speech processing systems. It describes how long it takes for sound energy to decay by 60 decibels in a room. Accurate T60 estimation is important in applications like speech recognition, enhancement, and dereverberation. Traditional estimation methods rely on non-impulse response and fixed-length input. But in real-world scenarios, the impulse response is usually unavailable and input lengths vary. In 2015, the acoustic characterization of environments challenge was established to identify effective blind T60 estimation methods and provide real noisy reverberation speech data for evaluation. Deep learning-based methods have been proposed for blind T60 estimation, achieving state-of-the-art performance on ACE evaluation. To handle time-varying scenarios, a convolutional recurrent neural network (CRNN) has been proposed to estimate the T60 binary from reverberant noisy speech. The CRN architecture used in this project includes 6 convolutional layers, each followed by ReLU activation and batch normalization. Then the extractive features are passed to an LSTM layer, followed by max pooling dropout and a time-distributed fully connected output layer. This architecture allows the model to process variable length inputs and produce T60 prediction in real time. To match the ACE challenge evaluation set, I synthesized a training dataset with the following structure: 7 rooms, each with 10 microphone positions, totally 560 source mic pairs. The source mic distance ranged from 0.7 to 3.5 meters in edge steps. T60 values vary from 0.3 to 1.5 seconds in 0.1 second increments. Then I mix the convolved speech with ambient, fan, and babble noise at SNR of 0, 10, and 20 decibel. Speech data came from Libre Speech, and artificial room impulse was used to simulate the room acoustics. Finally, the T60 values were refined using nonlinear least squares optimization to improve accuracy. Here we can hear the example from Libre Speech. Here's the before I mix with the noise.
The clock struck 12, and it still rained. You will not be able to go, my dear. I do not quite despair yet. I shall not give it up till a quarter after 12.
Then we can hear about uh, after I add some noise and the room acoustics.
The clock struck 12 and it still rained. You will not be able to go, my dear. I do not quite despair yet. I shall not give it up till 12:15. The clock struck 12 and
Before feeding the data into the model, I apply several preprocessing steps. First, audio was resampled to 16 kHz and truncated to 4 seconds. Then passed through an A-weighting filter to simulate human hearing sensitivity. A 21-band gamma tone filter back from 400 Hz to 6000 Hz was applied to extract frequency-specific energy. Energy was computed using 64 samples window with 32 sample hub. Finally, the features was standardized. I subtracted the median for each band and normalized the entire matrix to zero mean and unit variance. The result was a 21 by 1999 feature matrix for each input. The model was trained using the AdamW optimizer with a learning rate of 0.001. The loss function was mean square F. Here we can see the loss function. Training ran for 100 epochs, using 35,000 samples for training and 2,000 for validation. Finally, the CRN was trained to minimize error over multiple time steps, with the final estimate taken from the last output of LSTM. On the ACE evaluation set, my CRN shows strong performance. Better estimation accuracy and a higher Pearson correlation. Here's my result and here's the original paper's result. And the figure below shows the estimation errors on ACE evaluation by my CRN as can be seen. Better performance can be observed in the range of 0.3 to 0.6 seconds. Estimation becomes harder at higher second because longer decay requires more context for accurate prediction. The result align closely with the findings in the original paper. In summary, the CRN model successfully improves the accuracy of client T60 estimation under ACE conditions. In the future, there are two directions I plan to explore. First, replacing the CRN with a transformer-based model, which may better handle long-term temporal dependencies. Second, optimizing the architecture for real-time deployment in practical systems, such as speech enhancement on embedded devices. That concludes my presentation. Thank you for listening.